Hi, today we're going to be looking at redox reaction. Now, a lot of people don't understand this, so let's break it down to you. Remember, I teach simple principles so that we can apply them into the chemistry situation. So we're going to be looking at redox reaction. So of course, it's going to be a chemical reaction, but from the word redox, there are two words that are involved. The first word is red, that means reduction. The next word, ox, is oxidation. Define reduction. So what reduction is a decrease in oxidation number. Now this word is important. What is oxidation number? Oxidation number is like the charge. We're going to get back to that later. So know that reduction is a decrease in oxidation number, or we can also define reduction as a gain of electrons, right? We're going to look on oxidation now. Oxidation is a increase in oxidation number, and it's the loss of electrons. So there are two ways that we can define reduction and oxidation. One is in terms of oxidation number. If we're defining them in terms of oxidation number, a decrease in oxidation number is a redox reaction, and increase in oxidation number is an oxidation reaction. We can also define the two terms in terms of electron, what is happening. Now, in terms of reduction, reduction is the gain in electron, and in terms of oxidation, oxidation is the loss of electrons. So we're going to go into oxidation reaction, but before we get to oxidation reaction, we need to go back to the beginning of chemistry, the original principle of chemistry, to see what is happening. Now when we go there, we're going to look at metals. Remember we said that metals have 1 to 3 valent electrons. That means it have 1 to 3 electron on its outer shell. Because it has 1 to 3 electrons on the outer shell, metals are going to be unstable. So in order to become stable, metals need to have a filled outer shell. And to do this, metals are going to lose their valent electrons. Metal will lose their valent electrons, and when they lose the electrons, they are going to form cations, right? So they form cations by losing X electron, and they will form cation. No, X represent whether it is they're going to lose 1, 2, or 3 valent electron, and then the cation now is going to be charged positive the number of electrons lost, and we represent this by using this notation Mx plus. So let's go again. Metal will lose their valent electrons to form metal cations. So this is the symbol of the metal. X represents the number of electrons lost, and if they lose 1, 2, or 3 electrons, their charge is going to be plus the number of electrons lost. So let's go. Remember, metals lose their valent electrons to form Mx plus. So in the first example, we want to look on sodium. Sodium belongs to group 1, so of course sodium is going to lose how many electrons? It's going to lose 1 electron. So sodium will lose 1 electron to form Na plus charge, right? Now, magnesium is going to lose. Magnesium belongs to group 2, so magnesium is going to lose 2 electrons. So magnesium will lose 2 electrons to form Mg. And remember, the charge is positive, the number of electrons lost, right? Aluminum is in group 3, so it's going to lose 3 electrons, so its charge is going to be positive, the number of electrons lost, so it lost 3 electrons. So let's go. Sodium is in its elementary state. So if we look at sodium, we're not seeing any charge or any oxidation number. And we know that sodium is neutral, so the oxidation or charge on the sodium atom is going to be 0. The charge on it is plus 1. So in terms of oxidation number, right, sodium oxidation number increased from 0 to +1. So this is a oxidation reaction. Magnesium oxidation's number increased from 0 to +2, so magnesium is oxidized. Aluminum oxidation number increased from 0 to 3+, so aluminum is oxidized. Let's look on it. Every time there is an increase in the oxidation number, this is as a result of a loss in electron. So let's go again. Oxidation is either 1, an increase in oxidation number, or oxidation is simply a loss in electron. Magnesium lost 1 electron, and so its oxidation number increased from 0 to +1. Let's look at aluminum. Aluminum lost 3 electrons, and as a result, its oxidation number increased from 0 to +3. So nonmetals have 5 to 7 electrons on their last shell. Because remember, nonmetals can have 48 electrons. So we're going to talk about the ones that have 5 to 7 electrons on their last shell. They will gain electrons in order to become stable. And remember, gaining electron is a reduction. So let's go. This is what is happening. Your nonmetal is going to gain electrons to complete their outer shell. So if they have 5 electrons on their outer shell, they're going to gain 3 electrons to complete. Their charge is going to be negative the number of electrons gained, right? So it's going to be -3. So this here is not nitrogen, it's nonmetal. So that's what's happening there. So this N stands for nonmetal, right? The ones with 6 electrons on their outer shell are going to gain 2 in order to become -2. The one with 7 on its outer shell will gain 1 in order to get a charge of -1. So remember we said in a redox reaction, right? We have reduction and oxidation taking place, but there are principles to determine whether or not a reaction is really a redox reaction. These are the steps that we must know. Let's go. The first thing is that we need to calculate the oxidation number of all the atoms or ions in the reaction, not the compound, in the reaction. So we're going to determine them. So on the left hand side of the equation, what's your oxidation number? When you get to the right hand side of the equation, what's going to be your oxidation number? Once we determine that, we need to identify which atom is reduced and which is oxidized. Remember, the reduced one undergoes a decrease in oxidation number. The oxidized one undergoes an increase in oxidation number. So it means then that what we need to do is to first solve this problem here. How do we work out the oxidation number? That is the biggest challenge. Once we're able to work out the oxidation numbers, we have absolutely no problem. We're going to work out oxidation numbers. So the rules in calculating oxidation number is as follows. This is the first one. So rule number 1. All substances, whether they're in their elementary state, will have an oxidation number of 0. So if I'm going to react magnesium with HCl, right? I know that that forms magnesium chloride and hydrogen gas. I'm gonna balance that. I don't have any state symbol, so let's go. Magnesium in this equation, because magnesium is in its elementary state, magnesium is going to have an oxidation number of 0. Hydrogen, because hydrogen exists as a diatomic molecule, hydrogen is in its elementary state, so the oxidation number of hydrogen is going to be 0. So let's say if we had chlorine gas, the oxidation number is 0. If we had oxygen gas, the oxidation number is 0. If we had zinc metal, the oxidation number would be 0. If it was aluminum, it would be 0. Once they are by themselves in their elementary state, their oxidation number is 0. Step number 2 says that the charge of a monatomic ion tells the oxidation number. So let's go through this. Whatever the charge on the ion is, the oxidation number is the same as the charge. Let's review simple chemistry. Elements in group 1 we say they're going to lose one electron and their charge is going to be positive, the number of electrons. So it means their oxidation number is positive 1. What are the elements in group 1? Lithium plus, K plus, Na plus. This means anytime we say lithium in a compound, potassium or sodium, their oxidation number is equal to plus 1, which is their charge. Let's check group 2. Group 2 elements lost 2 electrons, so their charge is positive. The number of electrons lost positive 2. Example is magnesium 2 plus and calcium 2 plus. So whenever you see magnesium or whenever you see calcium, their oxidation number is always going to be, yes, plus 2. Elements in group 3, such as aluminum, loses 3 electrons to become stable, so the charge is positive 3. So if the charge is positive 3, the oxidation number is going to be, yes, positive 3. Good. So positive 3, such as aluminum, A plus. Now elements in group 4, group 5 and group 6 can exist in multiple oxidation states. So we're not going to study those, but those in group 7 are going to gain what? They're going to gain 1 electron to become stable, and their charge is going to be negative the number of electrons gained, so it's negative 1. So we have Cl minus, Br minus, and I minus. So elements in group 7 are going to gain 1 electrons to become stable. So for example, chlorine, its oxidation number is going to be negative 1. Bromine, negative 1, and iodine, negative 1. So let's review. The charge of a monatomic ion tells the oxidation number. This is it. The oxidation number of hydrogen is always going to be plus 1 except in metal hydride. In metal hydride, the oxidation number of hydrogen is going to be negative 1. Example. What do I mean by this? In ammonia, because it's not combined with a metal, in ammonia the oxidation number of hydrogen is going to be plus 1. In sulfuric acid and all other acid, the oxidation number of hydrogen is always going to be plus 1. In water, the oxidation number of hydrogen is going to be plus 1. In hydrogen peroxide, the oxidation number of hydrogen is going to be plus 1. However, in metal hydride, where hydrogen is bonded only to one metal, so it's only hydrogen and the metal, sodium and the metal, sodium and hydrogen, magnesium and hydrogen. In all of these cases, the oxidation number of hydrogen is negative 1. So when hydrogen combined with a metal, its oxidation number is going to be negative. The oxidation number of oxygen is always going to be negative 2, except in the peroxide where it is negative 1. So in every compound where you meet oxygen, you're always going to say the oxidation number of oxygen is negative 2, except if it is a peroxide. So let's go. Oxygen in this compound is not a peroxide. Oxygen oxidation number is going to be negative 2. Oxygen in nitrogen dioxide, its oxidation number negative 2. Oxygen in carbon monoxide, its oxidation number negative 2. However, in peroxide, hydrogen peroxide, the oxidation number is negative 1. But in all other cases, apart from the hydroxide, the oxidation number is always going to be negative 2. In the peroxide, it's going to be negative 1. So the sum of oxidation number of all the atoms in a polyatomic ion is equal to the charge. What do I mean by this? Let's go. This is a polyatomic ion made up polyatomic ion is made up of more than one atom. So in this case, this is the ammonia ion, which is NH4 plus 1. The charge is plus 1. So when you add the oxidation state of nitrogen plus 4 hydrogen, you're going to get the oxidation number equal to positive 1. So the oxidation number, the sum of oxidation number of all the atoms are going to be equal to the charge on the ion of the ion. So let's go. We are going to look on sulfate ion, and the charge on the sulfate ion is negative 2. So when I add 1 sulfur plus the oxidation number of 1 sulfur plus the oxidation number of 4 oxygen, I'm always going to get that equal to negative 2. Let's go. Dichromate ion Cr2O7 2 minus. When I add 2 Cr plus 7 oxygen, the oxidation number is going to be negative 2. So 2 Cr plus 7 oxygen, the oxidation number, when you add all of these, oxidation number will be equal to negative 2. In this situation, they could ask you to calculate the oxidation number of nitrogen in this compound. Remember, I tell you that elements in group 4, 5, and 6 can exist in multiple oxidation states. So let's go. We want to calculate the oxidation number of nitrogen. So nitrogen is unknown. I'm going to write that back. But I know the oxidation number of hydrogen is always plus 1. Except in metal hydride, this is plus 1, is going to be equal to plus 1. So N, 4 times positive 1 equals positive 4 equal positive 1. I want to get N by itself, so I'm going to be subtracting by 4. So I'm going to have N plus 4. I want to get rid of that. So I'm going to minus 4. What I do on one side of the equation, I must also do on the other side of the equation. So this is going to be minus 4. That cancel out that. So N equals negative 3. So the oxidation state of N is equal to negative. We could be asked to determine the oxidation number of sulfur in the sulfate ion. So remember, the sum of all the oxidation number of all the atoms in a polyatomic ion is equal to the charge. So 1s plus 4 oxygen, the sum of these oxidation number is going to be negative 2. So we want to find s, we write back s plus 4. 4 oxygen is always minus 2. 4 multiplied by negative 2 equals negative 2. So s minus 8 equals negative 2. We need to get s by itself. So in this scenario, we are minusing s. To get s by itself, we're going to add back 8. And what we do on one side of the equation, we will do on the other side. So I'm going to add 8 right here. When I add 8, this goes away. So s is going to be equal to 6. But we can't write 6, we must say positive 6. 2O7, 2Cr plus 7O equal negative 2. 2Cr is what we want to find. 7 times negative 2, because oxygen is always negative 2. So we want to say oxygen, the oxidation number for this is negative 2. So equals negative 2. So 2Cr minus 14 equals negative 2. Here we want Cr by itself. So 2Cr minus 14. To get rid of 14, we're going to add 14. What we do on one side of the equation, we will also do it on the other side. So we're going to add 14. This is going to cancel this. So 2Cr equals, I'm writing back this. So 2Cr equals negative 2 plus 14 equals positive 12. So I want to get rid of the 2 and multiply by 2, so I must do the opposite. So I'm going to divide this by 2. What I do on one side, I must also do on the other side. So Cr equals positive 6. Last rule. So we're at the last rule. The last rule says the sum of all the oxidation number in a compound is equal to 0. So a compound, remember, compound have no charge. So let's go. In this scenario where we have NO2, when we add the oxidation number of 1N plus 2 oxygen, the sum is going to be equal to 0. When we have sulfur trioxide, when we add 1S plus 3 oxygen, we're going to get 0. If they ask us to determine the oxidation number of N, so N plus 2 times oxygen, 2 is always negative 2, is equal to 0. N plus 2 times negative 4 equals minus 4 equals minus 4, 0. Right? We want to get N by itself, so we're going to say N minus 4. To get rid of minus 4, we're going to add 4. What we do on one side, we also do on the other. So I'm going to add 4. This cancels this. So N is equal to positive 4. S in this scenario, S plus 3 times negative 2 equals 0. S 3 times negative 2 equals minus 6 equals 0. I want to get S by itself. So over here I'm minusing by 6. In order to get rid of it, I must add 6. What I do on one side, I must also do on the other side. So when I do that, S is equal to positive 6. So remember, in a redox reaction, what we're basically going to do is we're going to first determine if a reaction is redox by first determining the oxidation number of all atoms are in the reaction, right? So we want to determine the oxidation number of all of these substances, and then we're going to identify what is reduced, what decreases in oxidation number, and what is oxidized. So let's go. In this scenario, magnesium is in its elementary state. So of course, by itself, magnesium is 0. Hydrogen is in this compound. Hydrogen is always plus 1. Chlorine is always minus 1. And magnesium in a compound is always going to be plus 2. Cl is going to be negative 1. I'm not interested in how many chlorine is there. Notice I'm only concerned about the oxidation number of 1 chlorine. The oxidation number of 1 chlorine is going to be minus 1. Hydrogen is in its elementary state, so its oxidation number is 0. So that is fine. The next thing we need to do is to identify what is reduced or what is oxidized. So in this scenario, magnesium moves from 0 to plus 1. So it means that magnesium is oxidized. Why is magnesium oxidized? Its oxidation number increases from 0 to plus 2. Let's go. Hydrogen moves from plus 1 to 0. So it means then that hydrogen is reduced. So HCl is the compound that the hydrogen is in. Hydrogen HCl is reduced since hydrogen oxidation number decreases from plus 1 to 0. Let's look on chlorine. Chlorine moves from negative 1 to negative 1, so chlorine remains the same, so nothing is happening there. So what is reduced? HCl is reduced since hydrogen oxidation number decreases from plus 1 to 0. Magnesium is oxidized since its oxidation number increases from 0 to plus 2. So in this reaction, we have copper sulfate reacting with zinc that is going to displace. So zinc is going to displace copper. It's a single displacement reaction to form zinc sulfate and copper metal. So remember, we need to determine the oxidation number of all atoms in the reaction. However, my sulfate remains intact on both sides, so I'm going to treat it as one entity. I'm just going to call the sulfate the charge on the sulfate. So what do I mean by this? Copper is going to be plus 2 in copper sulfate. That's the oxidation number. Sulfate is negative 2. So this is the one for that, and then this is the oxidation number for that. Zinc is in its elementary state, so its oxidation number is 0. In this compound, the oxidation number of zinc is going to be 2 plus, because the charge on zinc is 2 plus, and sulfate is going to be minus 2, Copper is in its elementary state, so its oxidation number is 0. What is happening? Copper is moving from +2 over here to 0, so the oxidation number is decreasing. So copper sulfate solution is reduced since copper, more specifically, since copper oxidation number decreases from +2 to 0. Let's look on the sulfate ion. In sulfate, we're moving from -2 to -2. Nothing is happening in terms of oxidation number, so that is either oxidizing or reduced. Let's look on zinc. Zinc is moving from 0 to +2, so the oxidation number of zinc is increasing. So zinc is oxidized. Why is it oxidized? Since Zn oxidation number goes up from 0 to +2. Alright, so let's go. We want to know, say, so this is a general fact. The substance which is reduced is always going to be the oxidizing agent. So whatever is reduced is going to be the oxidizing agent, right? Whatever is oxidized is going to be the reducing agent. So in this scenario, we could say copper sulfate is the oxidizing agent, and in this scenario, we say zinc is the reducing agent. So whatever is oxidized is whatever is oxidized is the reducing agent, whatever is reduced is the oxidizing agent. So we're going to be looking on oxidizing and reducing agent. Now what the reducing agent is the substance that is oxidized. So once we know what is oxidized, whatever is oxidized is the reducing agent. So again, we will define the reducing agent as the substance which increased in oxidation number. We would define the reducing agent as the substance which lost electrons in order to become stable. When we speak about the oxidizing agent, no, the oxidizing agent is the substance that has been reduced. It underwent reduction. What do we mean by that? It is the substance or the chemical or the element which is going to decrease in oxidation number. The oxidizing agents will gain electrons. Alright, so in this question it says identify the oxidizing agent and the reducing agent. So of course, you know, we're going to have to identify the oxidation number of all the substances in the compound. So let's go. Let's say we know oxygen now is +2, but we don't know what iron is in this case. So we're going to say Fe, 2Fe plus 3O is equal to 0. So 2Fe we don't know equals 3 plus 3 times -2 equals 0. So the oxidation number is -6. 2Fe equals 0. To get the value of 1 for 2Fe minus 6. We want to get rid of the -6, so we're going to add 6 equals 0 to plus 6. We're going to add 6. So to do that, this cancels out. So 2Fe equals plus 6. We want to get the value of 1Fe, so we're going to divide by 2, what we do on one side. So Fe in this scenario equals plus 3. So in this compound, Fe, we don't care how much is in there. We know 1Fe is plus 3. Oxygen is always -2, so we're at -2 there. In this scenario, let's say we want to find out the value of carbon in carbon monoxide. We're going to say C plus 1 oxygen is equal to -2 equals 0. So C plus -2, plus times -2 is equal to -2 equals 0. We want to get C by itself, so we're going to add 2. What we do on one side, we will also do on the other side. So we're going to get rid of that. So C is equal to plus 2. So in this scenario, the oxidation state of carbon is plus 2. The oxidation state of oxygen is minus 2. In this scenario, iron is in its elementary state, so the oxidation number of iron is 0. The oxidation number of carbon in this compound is going to be, I'm going to do a shortcut. So in this compound, we have 2 CO2, the sum of all the oxidation numbers are going to be equal to 0. So if I have 2 oxygen is going to be equal to -4. So this must be +4 in order to cancel that out. So I'm going to just catch this right here. In case you're confused, let me work it out for you. 1 oxidation, carbon plus 2O is equal to 0. C, 2 times -2, because the oxidation number is always -2, equals 0. C plus -4, equals 0. To get rid of the 4, we want C by itself. We're going to add 4. When we add 4, what we do on one side, we must also do to the other side. So C will be equal to +4, right? So C is +4 and oxygen is always -2. So the question originally asked us to identify the oxidizing and the reducing agent. But we need to know that the oxidizing agent is the substance which is reduced. So we're going to go to the equation and find out what is being reduced. So Fe moves from +3 to 0. So it means that Fe2O3 is reduced. So it is the oxidizing agent since it is reduced, right? The oxidation number of Fe decreases from +3 to 0. So whatever is the reducing agent now, the reducing agent equals the substance which is oxidized. So let's find what is oxidized. We're going to look. Oxygen moves from -2 to -2 over there. So the number remains the same. Nothing is happening to that. Let's look on the next compound. In this compound, it's carbon and oxygen. Remember, oxygen is the same. So let's go. Carbon, however, moves from +2 to +4, so carbon is oxidized. So the reducing agent is CO gas is the reducing agent. Carbon monoxide is the reducing agent since it is oxidized. The oxidation number of carbon increases from +2 to +4. Looking on oxidizing agents right now, and remember we said oxidizing agents are reduced. There are some substances which are just natural oxidizing agents. Examples of those are acidified K2Cr2O7, so this is potassium dichromate. When potassium dichromate is behaving as an oxidizing agent, this is what always happens. It always has a color change from orange, so it moves from orange to green, right? This is what happened. So remember that itself, it is reduced. So when it is orange, right, Cr is +6. So it moves from +6, where it is orange, to Cr +3. Alright, George, where it is green. So let's go. The oxidation number of chromium when it is orange is +6, and it is going to green where it is +3. Its oxidation number is decreasing. So Cr is moving from +6 to plus 3. When that happens, Cr is reduced, so this is a known oxidizing agent. Acidified potassium permanganate, is also another oxidizing agent. When acidified potassium permanganate is acting as a oxidizing agent, it has this color change. It moves from purple to colorless or pink. When it is purple, manganate is plus 7. When it is pink, it's going to be plus 2. So the oxidation number of manganate is moving from plus 7 to plus 2. So M moves from plus 7 and it goes to M plus 2. In order for that to happen, it means that it gained electron. So it's going to gain 5 electrons to form M2 plus. So let's go again. When it is purple, dichromate is plus 5. When it is colorless, it's plus 2. They ask you to write half equation. Simply, you're going to just indicate how many electrons is lost or gained. And we already know once the substance is reduced, the substance gained electron. So potassium, so the half equation is Kmn plus 7 plus 5 electrons is going to give me Mn2 plus. Let's look on this one, the dichromate. Dichromate, we said earlier, moves from plus 6 and it goes to form Cr plus 3. In order for that to happen, it must gain electron, because reduction is a gaining electron. It's going to gain 3 electrons, so that's the half equation. Ready? So here we are, we're going to be looking at reducing agents. And we say reducing agents are themselves oxidized. Here is a common reducing agent. We have Ki. When Ki, potassium iodide, is behaving as a reducing agent, it undergoes this color change where it moves from colorless to red-brown. I minus is the iodide ion, and in the M is going to be colorless. When it forms I2 is when it's red-brown. So that's what happened. The oxidation number of iodine moves from -1 to 0. And because it's moving from -1 to 0, it is oxidized. So because it is oxidized, it is of course our reducing agent. So let's go. What is the half equation for this? Because I2 is formed, we need to have 2I minus, right? And it's going to, in oxidation loses electron. So it's going to lose 2 electrons to form I2 aqueous. So this is what is happening. When it behaves as a reducing agent, Ki moves from colorless to red-brown. When it is colorless, Ki is -1. When it's red-brown, it's 0. So the oxidation number of I is increasing. So Ki is actually a reducing agent because your reducing agents are oxidized. So the oxidation number goes up. Iodine loses electrons to 2I minus 2 electrons form I2 aqueous.